Hi, welcome to the last session on subspace topology. I think this is the fifth possibly, and the main result today is what are known as gluing or pasting lemmas. Usually it's just done in a very quick way, but we'll go slow. I will also give some simple-minded but typical applications where you will usually find it in topology. Okay, but it's a very useful version. It's used to in topology and analysis, etc. Okay, so let us go ahead. Yeah, so gluing or pasting lemma. I usually call it gluing, but I think Monkress calls it pasting lemma. And this is the fifth session on subspace topology, and the references are the same. See, can you believe this? Okay, my YouTube channel is this, and I suggest you may download the list of videos which are available in my channel from this space. The reason is YouTube channel doesn't have its arrangement of videos is extremely difficult, maybe chronologically, but it's difficult to search for some videos. Okay, so this will give you arranged according to the topic with serial analysis. Then it will be something like a number system and sequences, continuity. Similarly, topology, okay, topology and examples, continuity, and let's say subspace topology, compactness, connectedness, like that. So in each topic it will be arranged according to the order, so it's better to download and learn from this. Okay, all right, so let us get started. Let me just make sure the video is on. Yeah, so what we have, suppose I have a set, just X is a set, okay, and suppose AI is a collection of subsets, so that union AI, I suppose I is an indexing set equal to X, and suppose I have a function Fi from AI to Y. Y is some other set, right? So how do I look at it? So look at it, this is the way, this is my X, okay, this is my A1, and this is my A2, and this is my A3, this may be my A4, and so on. You get the idea right now. I don't know to keep drawing all the pictures. Okay, these are the thing. Now I have a Y here, right? So this is my Y, okay, and from here this is my A, so I have a function A1, I have a function F1, and here I have F2, and this is A2, I have a function F2, and so on, and I have this A3, I have a function F3, and so on, right? Now what is the question I want? I want to know how I can glue them together. Idea is how to glue. Can we glue them together to get a function f from x to y in such a way that if I restrict f to ai, I should get fi. Yeah, right. So immediately you will see the one necessary condition. What is the necessary condition? Suppose ai I not equal to j, let us say if ai intersection aj is not empty, if I have an x, then fx should be fy of x, because x is in ai, it should also be fj of x when x is in aj, right? But I want f to be a function, that means f of x should be well defined. So what is the necessary condition? So necessary condition is the following: for all I and j, okay, fy of x should be fj of x for every x in ai intersection aj. Remember, if ai intersection aj is empty, there is no condition, so don't worry about it. I don't know to emphasize ai intersection aj is non-empty. If it is empty, of course it's true. Okay, so the important thing is, whenever there is an intersection, these functions take the same value. Fi and fj take the same value. Do you understand this? Then now we define f from x to y simply by saying f of x equal to fi of x if x belong to ai. Okay, notice that since x is union ai, given x in x, then there is at least one I such that x belong to ai. So I will simply define ai of x, f of x to be fi of x. But suppose x belong to aj, then I have to define fj of x, but our condition is, necessary condition is fi of x equal to fj of x, since x lies in the intersection of ai intersection aj. Therefore I get, therefore f is a well defined function from x to y. Okay, pause, review and proceed. Okay, there is a very stupid reverse process. Yeah, okay, a very simple reverse process. Suppose x equal to union ai, I in I, okay, where i's are of course subsets, and f is a function from x to y, then I define fi from ai to x such that fi of x equal to f of x. Alright, now notice that if x belong to ai intersection aj, then fi of x equal to f of x, but it's also equal to fj of x. Yeah, right. So have you understood this? This second process is a kind of, in some sense, reverse of gluing. You are kind of cutting them out and separating them out. Okay, it's a kind of decomposition. Whereas the earlier one is gluing process. I have fi on each and every subset, but the union of the subsets is the full set. Then I want to glue them together as to get a single well defined function from x to y. Okay, right. Now let us look at what is the analog of this in the context of topologies. In the context of topology. So what condition do you think I should ask for? So I am going to assume x tau is a topological space, maybe if you want to make it curve, and y tau y is a topological space. Right? Then what am I going to do? Let ai be a collection of subsets for each I and I, so that x equal to union ai. Right? Okay, now what are ai? ai's are given the subspace topology. Let me write it. Tau I is the tau of ai, that is the subspace topology on ai. Right? So what is the analog question I am going to ask? Let fi from ai tau I to y tau y be continuous for all I. You understand that? Now what is the question? Can I glue them together to get what kind of function? Of course a continuous function. Continuous function f from x to y. Okay, is that clear? Alright. Okay, now the first thing is, set theoretically to get a function we already know there is a necessary condition. What is the necessary condition? So necessary condition is is assume for all I and j, okay, fi of x equal to fj of x for x in ai intersection aj. This is a necessary condition. Then only once I have this, we then have a well-defined function. F from where to where? The set x to the set y. So set theoretic is just a function from two sets. This I already explained. Right? Now I want to know, okay, will f be continuous? So I got a function. Notice that this is the unique way you can define the function. There is no other way you can define the function. Do you understand that also? Okay. Note that. This is just a set theoretic thing. I should have mentioned that. Okay. That is, what does it mean? If I have a function g from x to y such that g restricted to ai equal to f5 for all I, then g must be equal to f. Right? So there is no way out. Okay. So you glued the function, which is family of functions fi, which satisfy the necessary condition to get a function from x to y. Right? So now I got a function as required. Now the question is whether it's continuous. So let us check. How do I check continuity? Okay, there are two ways. One is look for open set. So let us look at the first way. Okay, let b be in tau of y. Okay, open. Then what should I have? F inverse of b. I want to know whether it is in tau of x. This is a question. Right? Then f will be continuous. But let's look at what is f inverse of b. What is f inverse of b? It is set of all x in x so that fx belong to b. Right? But f inverse of b, notice that this is b intersection x. But this is f inverse of b intersection a union I. Yeah, because this is, we had already seen such things, so don't ask me to explain. Okay, this is same as union I in I of f inverse of b intersection a. Right? Therefore, let me rewrite. So f inverse of b is union I in I of f inverse of b intersection ai. Okay, make sure that you understand. Okay. Those of you who are not very sure, to check this. Okay, take x here on the left side, prove it's on the right side, and take x in the right side and prove it on the left side. Okay, this I have done many times in this course, topology course, because I find that students are not very conversant with the basic, this kind of inverse images, etc. Okay, I have done it, so I am not going to do it now. Okay, now let us look at what is f inverse of b intersection ai. This is nothing other than set of all x in ai so that fx belong to b. Right? But this is same as, since x is in ai, f of x is same as fi of x. Right? But this is same as fi inverse of b. You understood that? Yeah? Make sure you understand. Right? Again, if you want a picture, you should have a look picture. This is my thing. This is my I. Let us say simply two things. This is my y. Okay, I have a v. Okay, when I take the inverse image, that's going to be something like this. And there may be something. This is one set. This may be another set. This may be a third set. Okay. So these may be the ones which constitute f inverse of b. You follow that? Okay. Therefore, I have F inverse of V is nothing other than Fi inverse of V I varies over I. Okay. Pause. Review. Proceed. Now, what is that I wanted? Okay. I wanted them to be this. I wanted to be open, since V is open. So I want this to be open. Okay. That means this union should be open. So what is the easiest way to make sure this the right hand side, okay, is open? Yeah, a sufficient condition for the right side to be open. Remember, Fi inverse of V is open where? In tau I, not perhaps in tau x, because F is a continuous function from A to y. Therefore, F inverse of V will be open in tau I. But if you in the last lectures we proved something very interesting. What did you prove? If my AI is open, okay, then Fi inverse of V is open in AI if and only if it is open in X. Okay, recall this, we proved in the last lecture, right? Have you understood? Now you see that therefore what is that I have to do? So for case 1, okay, assume my A's are open. Okay, then what I have is F inverse of V is union I Fi inverse of V. These are open in tau I, but and hence they also belong to tau because A's are open. Now this is, and this is a union of open set, therefore this is open. Hence, okay, F inverse of V is open. Okay, so let's quickly go through this. So what I have proved? We have proved the following result, which is theorem 1, if you want. Okay, let x tau x be a space, and similarly y tau y, and let A I in I be a collection of open sets of x such that x equal to union A. Let Fi from A to, that is AI with the subspace topology tau I, let tau I be the subspace topology on AI to y tau I be continuous for all I in I. Okay, assume further Fi of x equal to Fj of x for all x in AI intersection Aj. Okay, then define f of x equal to Fi of x if x belong to x, which is union of AI. Then f is well defined continuous function from x to y. This is all we have proved. Okay, writing this takes more time, but you can see the analysis is very easy. Yeah. So set theoretically we have got the function. I have to show it is continuous. Let us go through the proof once again. Let's start with this. F inverse of V. This is set of all x in x such that Fx is in V. Right? But this is same as saying I can rewrite this as, okay, F inverse of V, I can rewrite as F inverse of V intersection union intersection x, that is F inverse of V intersection union A. Right? Therefore, if x belongs to this, that means this x must be in I, right? Therefore, this we see this is nothing other than union of F inverse V intersection I. But then remember, if x belongs to this I, then fx is nothing other than fi inverse of V intersection I. Okay, so this is immaterial now. Okay, just make sure this all I am saying, I am just repeating, even though I didn't want to, is nothing other than fi inverse of V. Let x belong to this, that means x belong to A and fx belong to V, right? But x belong to Vi, fx belong to A, the same as saying, okay, x belong to A and fi of x belong to V, because for x in A, f of x is fi, right? But this is same as saying, okay, x belong to fi inverse of V, because this is subset of A. So I proved that. Okay, now what do you know? Therefore my f inverse of V is union fi inverse of Vi. These are all open in tau I, but A's are open and this is open in Ai. Therefore it follows this is open in X, and f inverse of V is union of open sets. Therefore it's open. Okay, I had completed the proof. Go through, pause it. Right, now let's look at a second version. Suppose I start with a B, a subset of Y, so that B is closed, right? Then if by f to be continuous, then I want f inverse, so I want to know whether f inverse B is closed. You understand? Now exactly as I proceeded earlier, you will see that f inverse of B is nothing other than union of I in I, fi inverse of B. Okay, because whatever I did here, go through that, there is no continuity, nothing. This is just set theory. Okay, this portion is set theory. Continuity etc. comes only when I wanted to assert these are all open. Okay, I just want you to think along with me rather than give a proof so that you can easily memorize. Okay, you can always read your book and learn this kind of thing, but try to think. Okay, this is just set theory. Right, now what do I know? Since B is closed, fi's are continuous. Okay, so what do I know? I know that fi inverse of B is a closed set in A, right? Now what do I want? I want to know that this is closed. Okay, right, even if I know fi inverse of B is closed in A, okay, union of closed sets need not be closed in X, right? This is closed in A. Okay, it may not be closed in X. Assume it's closed in X. Then also it's arbitrary union, right? I do have no idea about capital I. It may be for infinite set. You understand that? So what are the things you should know? What kind of conditions you would like to impose? See, you are discovering mathematics. You see that I am not stating the theorem and then proving it. We tried to prove some, work out something, argue, then we arrive at the correct hypothesis. So if I want to say fi inverse of B, this is closed in A, but I want it to be closed in X, what is the sufficient condition? Like yesterday, so we have to assume each A is closed in X. Then fi inverse of B being a closed subset in A, but A itself is closed in X, therefore this will imply fi inverse of B is closed in X, right? Okay, so I got F inverse of B equal to union of Fi inverse of B. Each Fi inverse of B is closed in X, but it's arbitrary union, so I cannot conclude it is closed in X. So what is that? I have to put in another restriction. I have to put the restriction I must be finite. Do you understand? So if I is finite, okay, then F inverse of B equal to Fi inverse of B. Okay, these are all closed in X, and this is in a finite set. So finite inner of closed sets is closed, therefore F inverse of B will be closed. Right? So now let us understand what is the theorem 2. This is okay, second version. So what I am assuming now, let X tau y tau X y tau Y be topological spaces, and assume I is a finite set and A is a finite collection of what kind of sets? So that X is union A. Okay, if you want, you can now think of it A1 union A2 union AN, but that doesn't matter. Okay, then assume Fi or continuous function A tau Y. This is the subspace topology. This 2y tau y continuous for all I in I, and Fi of X equal to Fj of X for all X in A intersection Ej. Then define F of X equal to Fi of X if X belong to X equal to union of AI. Therefore it must be at least one I. Then what do I want to say? This is set theory. F is well defined function from X to Y, and F is continuous from X to Y. Okay, now we discovered the statement also. You see that beauty? This is how usually mathematics is discovered. You don't know it as a theorem. You just try to explore, try to ask, and try to attempt a proof. Then whatever is needed, you put it as a hypothesis, then rewrite it. Okay, now how will I write a proof? Proof is again the same. Let B be closed, then observe F inverse of B is union of F inverse of B okay, intersection with I and I. But then observe this I and I is Fi inverse of B, but this is closed in A and A's are closed in X, therefore this is closed in X. Each Fi inverse of B is closed in X, but this is a finite union, therefore finite union of closed sets, therefore F inverse of B, this is closed. You see that how simple the proof is? But what we did in both the cases, we arrived at it. Okay, so let us understand what I have shown now. We had a family of functions, we glued them together to get a function, well defined function with a necessary condition imposed. Okay, and after that we wanted to check the continuity. How did we check the continuity? F inverse of open set must be open, or F inverse of closed set must be closed. These are the two obvious conditions. So in each of the conditions I wanted to do. Okay, we got a theorem, right? Okay, now there is usually textbooks only deal with this aspect, but there is a kind of, it's like a coin, has two sides. So one side of the coin is what we saw, head we saw. There is a tail side. What is the tail side? Suppose I have function f from a topological space x tau x. This is never explained in textbooks. Please listen to me carefully. Okay, I want to know whether continuity, I want to check continuity of f. Right, notice that Please understand, this may be little vague. If x and y are very concrete, okay, this f, you may have a very explicit expression like Rn to Rm kind of thing. You may have a very explicit expression for f, right? And using that you want to check. Then what may happen is you may be able to find a family A of subsets of x such that x equal to union A, so that all A's are open or the family is finite and A's are closed. Okay, then then restrict f to A, call it fi. So if I check the continuity of fi, then I would have checked the continuity of f. Do you see that? We are again checking piecemeal. So I have this f, okay, from x to y. So I check it's continuous here, and I check it's continuous here, and I check with subspace topology continuous here, and I check this continuous here, right? Piecemeal. Then I know continuity of f. Do you follow that? This is never explained. You will be surprised. This is very useful. Okay. So pause, review, proceed. Okay. In fact, this is the version you will use often. Okay. You want the textbooks will say by gluing lemma or pasting lemma it follows. You will be surprised. This is the version. For example, let us start with the simplest case. Let f be from R to R. Right. Now let's look at the function f of x equal to mod x. What is this? Notice that f of x is x greater than x if x is greater than or equal to 0 and equal to minus x if x is less than or equal to 0. You see that? Now I have the function, the simplest example I am looking at. What is the simplest example? Let us look at fx equal to mod x. Alright? Okay. Now on the positive non-negative axis, including this is x, whereas here it is minus x, right? Now do you see that? You call this as, therefore my a1 is going to be 0 to infinity and a2 is going to be minus infinity to 0, closed. These are all closed. There are two sets, finite sets, and on f1, that is f restricted to a, f1 of x is nothing else than the identity function. Therefore this is continuous on a1. And similarly f2 of x equal to minus x, that's also continuous on a2, right? And what do I know? I start with the function f which is already defined and restricted. If you don't want what is a1 intersection a2? That is singleton 0, right? And on that they coincide. f1 of x is same as f2 of x, namely 0. Therefore I have the modulus function is continuous. Okay. Pause, review, proceed. I will give one more example. So let us look at Rn. Okay. Rn to Rn, okay, Rn minus 0 if you want. Okay, this is the usual topology, usual subspace topology if you want to say. These are all open sets in Rn. Okay, they are open sets, right? Now what I want to look at, I want to look at the function f of x equal to, yeah, just 1 second. Let me think. What do I want to do? I have this. I have an x. I want to map it here. Another map it here. Right. X by I don't know that that's the one I want, but let me just say whether this is continuous. Yeah, this is automatically continuous. So this is not what I want. Okay, I thought of a very nice example. Let me see. Okay, let's forget it. Okay, forget this. I'll come back. Okay, so let us look at a third example. Actually, this is going to be second example. Suppose I take 0 1, this is my x, okay, and this is my y, and by a path alpha I mean a continuous function from x to this y to tau y. Okay, so this is alpha at 0, this is alpha at 1. Okay, this is continuous, right? Now suppose call this is point P, this is a point A, this is a point B. Suppose there is another path connecting B to C. Okay, suppose beta is a path connecting B to C. Therefore, what do I have? I have alpha of 0 equal to A and alpha of 1 equal to B, and beta of 0 is B and beta of 1 is C. Right? Now if you look at the picture, you can see there is some kind of a path from A to C, namely you go via alpha like this up to B and then follow it up by this. But for me a path has to be a continuous map from 0 1 to that. Therefore what I am looking for is I am looking for a gamma from 0 1 to y tau y, so that I want gamma of 0 to be A and gamma of 1 to be C, and this must of course be continuous, right? So what do I do is this, I look at 0 to 1, okay, look at half. Okay, so think of this as a train, think of alpha as a train. At time 0 it starts at A, at time 1 unit of time it goes to B. Now what I want is I want the train to go twice as fast, that is in the half of the, that is at 0 it starts at A, at half it reaches already B. That means I have to go at twice the speed. So what I do is I define gamma t to be alpha of 2t 0 less than or equal to t less than or equal to half. So this is your A1. Okay, and A2, now within half the time I had reached B, then I take this second train beta. Okay, this is the train beta. Okay, I take the second train beta at the time equal to half I start from B, and at time equal to 1 I reach 1. So the same train beta, but now I have to go twice the speed. Okay, so I write it as beta of 2t minus 1. When t equal to half, it is 1 minus 1 0, it starts at B, and beta t equal to 1, it is 2 minus 1 beta 1, therefore it reaches C, right? Therefore notice that gamma of 0 is A and gamma of 1 is C. This is fine, right? I only have to check continuity of gamma, right? But continuity of gamma is easy, because now notice that gamma restricted to A1, which is 0 to half, have an explicit expression, namely the function t going to 2t going to alpha of 2t. Notice that for t between 0 and half, 2t will lie between 0 and 1, therefore it is in the domain of alpha. Okay, those things you have to check. Okay, now this is a continuous function. You see that now I have an explicit expression, therefore I know gamma restricted to this one is continuous. And similarly, let me restrict gamma restricted to A2. Okay, notice that this is half to 1, and what is the first thing there? It is 2 going to 2t minus 1, that's a continuous map, and beta is continuous 2t minus 1. Notice that for 2t between half and 1, this fellow belongs to 0 to 1, therefore beta of 2t minus 1 makes sense. Okay, these are the small things you should learn to check. Okay, I find many kind of big students who are struggling do not, because the teachers will very quickly write it and say it's continuous, and many students do not know what is there to check. Okay, we are checking all those things, right? You follow that? Okay, so I got a function, and do I know this is continuous? Again, gamma restricted to a2, call it if you want gamma 2, this is continuous, and gamma 1 here restricted to a1, gamma restricted to a1, call it gamma 1, this is continuous on a1, right? Now I want to know whether gamma is continuous. For that, what do I have to do? I only have to check gamma 1 of half. What is a1 intersection a2? That is singleton half. Okay, therefore I have to check whether it is same as gamma 2 of half. And remember, what is the domain for gamma 1? It is 0 to half. What is the domain for gamma 2? Domain for gamma 2 is half to 1. Okay, don't make it's not 0 to 1. So domain for gamma 2 is half to 1. Okay, right. So gamma 1 and gamma 2 are continuous on their respective domains a1 and a2. Very good. And then on the intersection, are they same? Yes, both are equal to b, right? Therefore by gluing lemma we know it is continuous. Is it okay? Right. Now what is the third one? The one which I wrote with x to norm x etc. I had forgotten. Just yeah, let me, I think now I got it, but let me see. This is example 2. F is from Rn to Rn itself, and f of x equal to x if norm x is less than or equal to 1 equal to x by norm x for norm x greater than or equal to 1. Okay. Now I want to know whether f is continuous. Right. Now again notice that. So what do I have? I have a1 which is norm x less than or equal to 1. This is a closed set. And a2 which is norm x greater than or equal to 1. This is again a closed set. Remember we had already shown in a closed ball in a metric space is closed. Okay. And since the open ball B01 is open, it is complement, namely norm x greater than or equal to 1, that will also be closed in Rn. So both are closed sets and their union is Rn, right? And when I restrict f to each one of them, it is continuous, because on a1 it is identity function, on a2 it is again identity function multiplied by a function 1 by norm x. X going to norm x is continuous, and on the set a2 it's non-zero, therefore 1 upon that is continuous, product of continuous function is continuous, therefore both are continuous. Now is it continuous on the whole? That's correct, but what is a1 intersection a2? That is set of all x in Rn so that norm x equal to 1, right? And therefore what is f1 of x? It is x. And what is f2 of x? That is x by, I think, norm x, right? But remember, if x is on a1 intersection a2, norm x is 1, therefore it's also x, right? Therefore what does it mean? This means, so I have this, everybody is here, but anybody outside here is mapped to this. Okay, he is mapped to this. This fellow is mapped to this vector. This fellow is mapped to this vector. Do you understand this picture? Yeah. So everybody is mapped into the unit ball. Okay. So now do you see that even though, so these are the examples, and notice that in all the three examples I had given, maybe I will switch over to video. Notice that in all the examples I had given, we used the gluing lemma when my A's are finite in number, they are closed. So one may wonder whether there is any application of gluing lemma when A's are open. Okay, believe me, there is very, very beautiful application of this. You can find it in my topology of metric space, where I want to show there is a continuous argument and R2 minus 1 closed half axis. Okay, if you are interested, please look into that. And that version is also very useful in analysis most often. It goes under various names also, but it's useful. Okay, I hope you enjoyed the lecture, and I hope you also appreciated. What did you appreciate? I am not very sure, because textbook always give gluing, that is fi's are given on a, you get a continuous function f on x. Okay, that's fine under various conditions. But what I said was very interesting. Okay, the tail part, namely I have a function f which is given on the entire domain. I want to check its continuity on x, but what I do is I do it piecemeal. I check the continuity of f when I restrict it to some either a finite number of closed sets whose union is x, or any family of open sets which cover x. That is the way we always used. Look at all the three examples. That's the only way I used. It's never brought out on textbooks. I hope you enjoyed the lecture. Keep safe. We'll meet again.